Okay, AP students, welcome back to the last lesson for electrochemistry, lesson 6. Just going to go through some addition and decomposition reactions. Many of our addition and decomposition reactions are actually redox. This is the last section of reaction prediction for the year, actually. So we'll go through and I'll do a few of them for you. This shouldn't take very long. There's some practice, I think, I don't know, 16 or so reactions for you to predict. Do the best you can. Some of them are a little difficult. Some of them are really straightforward and easy, but give them a shot. You likely will not have to predict products on your AP exam. We'll ask that you do a little bit of it on our end in our class, in our coursework, but on the AP test, you won't have to, but it'll be good practice for you to know kind of what to look for. Okay. Let's see. So we're going to start actually with decomposition reactions. So a decomposition reaction is where you have something or a single thing breaking up to make more than one substance. It could be elements or compounds. It is going to require something usually, not necessarily, but usually it requires something to happen, whether you add electricity through electrolysis or perhaps you add a catalyst, maybe you add heat. Something's decomposed automatically, though a catalyst helps make it go faster. But in a sense, it's just something that breaks up into two or more things. So here we have molten sodium chloride being electrolyzed. So I would have NaCl, and molten would be in the liquid state. You wouldn't have to necessarily say that. It is going to break up into solid sodium and chlorine gas, and you would go back and balance with some 2's there. This would be a solid. This would be a gas. No one is asking you to write the states of matter on these, but that's kind of the way it would be set up. You do not have to do this in half reaction method. You just are predicting products and balancing like we did, originally. And again, states of matter, if they're told to you what they are, usually you should put them in, but not necessarily. It's really not a big deal. And if anything is aqueous, you are certainly able to leave it out. Double replacement reactions, we generally want you to label the precipitate or any molecular compounds, but it's okay. So moving on, there are some other ones. You may have a compound that breaks up to produce an element in a compound. A good example is hydrogen peroxide. I think you guys know that hydrogen peroxide will break down into water and oxygen gas. Decomposed catalytically just means that you're having it go faster. You could write that you could write CAT up here for a catalyst if you prefer, but it's really not necessary. You come through and you balance this with a 2 and a 2, and you're kind of done with that. Again, if they gave you the catalyst, it would be a good idea to write it. So if they had said, catalytically with MnO2 used as the catalyst, you would put the MnO2 over the arrow. A compound may break down to produce 2 elements. So solid magnesium carbonate is heated. Magnesium carbonate's formula is MgCO3. It does say solid. I'll go ahead and label it anyway. And it's going to break down to produce magnesium oxide, which would be a solid, and CO2, which hopefully you guys know is in fact a gas. If I were heating it, I would draw a triangle above the arrow demonstrating that it's heated. If you didn't feel comfortable doing that, you could write the word heat above it, and that would be okay as well. So there are those 2 examples. So those are just examples of things that can happen. There are rules that go along with it. Some of these rules are going to be the same ones we've already done. Metallic carbonates break down to yield metallic oxides and carbon dioxide. That's one that we've already kind of shown you. Metallic chlorates break down to produce metallic chlorides and oxygen gas. Remember that chlorates are ClO3 minus things. So sodium chlorate, potassium chlorate, magnesium chlorate even, they're going to break down to make that metal with a Cl attached to it, a Cl minus, and oxygen gas. Hydrogen peroxide decomposes into water and oxygen. We've already had that one as well. These are these 3 examples. If you want to pause and write these down, knock yourself out. I'm going to go ahead and move on, but these are the same as the ones I did earlier. Ammonium carbonate will decompose into ammonia, water, and carbon dioxide. We say water and carbon dioxide actually kind of produces H2CO3, and the H2CO3 then breaks down, of course, into water and carbon dioxide. Sulfurous acid. So sulfurous acid is H2SO3. it will break down to make water and sulfur dioxide, and then carbonic acid, as I have already said over here, H2CO3 will break down to give you water and carbon dioxide. And those examples are here as well. If you want to pause and write these down, these are ones that we have had certainly in the past. So that takes us to addition reactions. In addition reactions, two or more things are going to come together to form a single product. Usually it's just two things, two elements or two compounds, or a compound and an element are going to combine to make a single compound. Now, if they are ionic compounds like we have here with magnesium and nitrogen, so I have a metal here and a non-metal here, these things are going to combine by their charges. So in the case of magnesium nitride, magnesium is 2+, nitrogen is 3-. Put your compound together, Mg3N2, like I already have written here, and then go back and balance it afterwards. So that's a little bit different. Here's a great example. A piece of lithium metal is dropped in a container of nitrogen gas. So lithium dropped in a container of nitrogen gas. This will be put together by charge. You could do it off to the side, if you can't see it in your head, but lithium and nitrogen are here. So my formula, if I switch these partners here, would be, oh, that's not an L, that's tragic. Lithium nitride like this. Then you would go back and balance it afterwards. So I would need a 2 here and a 6 here and balance that. Two nonmetals may combine to form a molecular compound here. Generally, we say they kind of squish together. The oxidation number of the less electronegative element is often variable depending on the conditions. Okay, so what you're going to look at is kind of its valence electrons. These are a little bit more difficult than what you're used to. I'll kind of show you how I think about them. But you have to kind of look at what their oxidation numbers are in order to figure these out. A good example of this is this phosphorus and or P4 and how it reacts with things. So phosphorus here, the P4 is going to have, phosphorus individual atom is going to have 1, 2, 3, 4, 5 valence electrons. To obey the octet rule under limited chlorine, chlorine is actually going to have a limited chlorine exposure, 7 valence electrons. Halogens are only going to form single bonds. And so this is going to form a bond right here. I would have another bond with a chlorine here, and that would make this PCl3. That's with limited chlorine. But because phosphorus can break the octet rule, if instead of having a limited amount, I have excess Cl2, it could have phosphorus forming a bond all the way around it, 5 bonds around it to different chlorines, right? So it'd have a bond there, bond, bond, and you would have chlorines everywhere. You actually could make PCl5. And so in that case, it breaks the octet rule, and every valence electron for phosphorus would have a pair of electrons, or it would be bonded, having a total of 10 electrons around it. That's a little bit harder to see for some of those. Another one that you'll see this happen with is sulfur. Sulfur is typically S8, and sulfur can form bonds with just 2 things. What is that nonsense? Anyway, sulfur can form with 2 things, or sulfur can form and break the octet rule with 6 things around it, having 12 total valence electrons. So you'll see some strange things with P4 and S8, but that's all right. When an element combines with a compound, you usually sum the elements on the product side. So if they, usually you'll just kind of push them together. That's not always true. You have to kind of look at the rules, but a lot of times it is. On the bottom here, 2 compounds combine to form a single product. In the case of sulfur dioxide passed over hot calcium oxide, you are having SO2, and in this case, a metal oxide. That's going to produce a metallic sulfite. So this is merely the rules backwards from what we did for decomposition. So for your PCl3Cl2, most of the time, you'll just squish all these nonmetals together. And you're doing that down here too, but the metal oxide SO2 is actually a rule. You would have the same thing, metal oxide and CO2. Now with boron trifluoride and ammonia, those are a little odd. Boron trifluoride is breaking the octet rule. Let's see if I got some room. I don't really. I'll write it up here. But like BF3 has 3 fluorines around it like so, and no lone pair of electrons. It breaks the octet rule going low. Whereas ammonia has hydrogens all the way around it, but it has a lone pair that could have used to donate as a Lewis base in a coordinate covalent bond. And so what it'll do is it'll just use those 2 electrons to allow a boron to obey the octet rule, and nitrogen as well. And it forms this compound of the 2 mixed together, which is interesting. And this is always the example that they use, or that I see for Lewis acid base theory. But that's actually what's happening there. Metal oxide and carbon dioxide, we already said this. Metal oxide and sulfur dioxide, we already said this. These are both reverse of the decomposition reaction. And then a metal oxide in water, this one is actually new. Metallic oxide would be something like, I don't know, sodium oxide, and you would add that to water. It's actually going to make the metallic hydroxide. It's going to actually produce a base. And so you balance it, of course, with the 2. Non-metallic oxide in water yields an acid. The non-metallic oxides in water, you're just going to push them together. So if I look at the ones that are down here, like sulfur dioxide and water down here, this one, you're just going to push these 2 things together because they're all nonmetals and make this. With the sodium oxide, you're actually producing a base. Now, this one could be in a limited amount of SO2. And we actually did this in the lab, where you guys took solid sulfur, you heated it in the fume hood with a Bunsen burner, and then placed it in pure oxygen, and it blew. It gave a really blue light as it ignited. That was in excess of SO. And then you took it, and put it in a vial with water, and you made an acid. It's likely that you had a mixture of both H2SO3 and H2SO4, depending on how much sulfur dioxide was actually there. So an excess of SO2 could actually produce, you could have also produced SO3, and then you would have H2SO4 as a result. So it could be a little bit different in that case. But that pretty much sums it up. So that's all of those. I know I went through them really fast. I apologize. Kind of the end of the year. We have done these before, but if you have questions, talk to your instructor. That is the end of our discussion for electrochemistry. I'll see you online for the lab that we'll do digitally, and that's it. All right, guys, it's been a good unit. Good luck.